are way up here is because they're pretty noisy. And you know, they're really good experiments, and everyone's doing their best, but this is a really small signal. Oh, I cut off the axis like this, but this is a really small signal. This is like microkelvin squared or something like that. So just getting to that sensitivity is a lot of work. And so if you want to tell the difference between noise in your map and some small fluctuations, it's not easy. But here, we actually know what to look for. And now you have a template. You can say, aha, let's go look for that. And that's what we did. So, and we did it a bunch of different ways. We took our E modes that we measured a bunch of different ways. We measured them at 150 gigahertz, at 90 gigahertz. You can actually guess what the E mode should look like from the temperature fluctuations. We have a bunch of different ways of estimating this gravitational potential. We can use the 500 microns. We can use our own temperature data. There's all sorts of ways to measure this. And that gives us a few different versions of this predicted B mode thing. And we just take this and we just look in our data to say, do we see this in our data? And indeed we do. If you do the predicted B and you compare that to what we actually measure, and you do an angular power spectrum again of the predicted B compared with the measured B, what you see is you see sigma. So it's a 7.7 sigma detection that our data has B modes in it. So we finally detected this signal. And yeah, we knew it was supposed to be there, it had to be there, but the way science works is if you know something has to be there, you should go prove that it's there, right? That's the scientific method. If you know it's there, you better measure it. And indeed it is there. So at 7.7 sigma, we've detected this gravitational lensing B mode signature. So it's sort of the first step towards marching down to measuring the B modes from inflation. But it's also a new way of measuring this gravitational potential. And so this is a paper that just came out in PRL, or I don't know if it's out yet, maybe it came out last week. And it was led by a postdoc at McGill, Duncan Hansen, and Stephen Hoover and Abby Kreitzer at Chicago, and then everyone else from Taiwan. So that came out last week or something like that. Okay, so here's a summary. So high resolution CMB maps are giving you new information about the universe. I hope you've got that out of the talk. Gravitational lensing is a powerful new probe, and so everything I've shown you is brand new. It's only happened in the last, the first detection of any of the lensing of the CMB was only 2008. So in 5 years, it's gone from sort of a 3 sigma detection to just making these large-scale maps over the whole sky. The lensing of polarization fluctuations has just been measured for the first time. In some ways, what I showed you right now is the first detection of the lensing of the polarization fluctuations. And I think sort of one of the most exciting things to come out of this is that the B mode frontier is now open. So B mode polarization has now been detected. For the very first time, it's a new form of polarization anisotropy. Has now been detected. And so all that we have to do now is just keep drilling down on that until we get down to the inflation rate. All right, I'll leave there.
Thank you very much. Questions?
Could you explain again why you can sort of enhance the signal to noise ratio by anticipating what the B mode looks like?
So basically, so what it comes down to is that this, as I showed you that map, the temperature maps, for instance, it looks almost like a noise field, right? It's just some random fluctuations. And not only does it kind of look like a noise field, it basically is a noise field. And so if you're just trying to detect the total power, you're basically trying to measure an excess of noise compared to what you expect to be there. And that's a really difficult thing to do because you have to somehow know exactly what your noise level is. And if you have a large amount of noise that's corrupting your signal, you have to subtract that out and then guess what the signal is. And that just that adds some inherent uncertainty to it. Whereas if you have some template to go against, there's still some amount of noise there, but it basically comes out to being that your uncertainty in this, if you do a template match, the noise in your maps comes in as the square root. So maybe that's the best way to think of it. So let's say you have 2 maps, and you want to cross-correlate them and see how well correlated they are. The noise in that comparison is going to be the geometric mean of the noise in the two maps. So if one of your maps, so if it's the same map, then you get the square of the square root, which means you get the full noise. If one of your maps is noisy and the other one is good, then you get the square root of noisy, which is better. Right? The square root of noisy is better than noisy. It's smaller. And if you have two good maps, well then the square root of good squared is good. So what it gains you is that you only get one power of your noise instead of two. Basically what it comes down to. So if you have some noisy signal, if you have a noisy map and a good map, and you want to tease that signal out, the easiest way to do it is just to cross-correlate those two with each other. And so this is why we were able to do this, even though our noise level is not much below. Actually, our noise level is very close to those B-mode searches that were done. Our noise level isn't substantially better than their noise level. It's just that we had a template, whereas they don't yet have good templates, although we're actually working with the BISAP people to do the same thing.
Generate templates for those
No, because we don't know what they look like. So this is the thing, is we have no idea what they look like. So if you're looking for something, so it's much harder to find something if you don't know what you're looking for.
In order to measure the B mode, which has a substantially smaller amplitude than E mode, one really has to worry about the leakage between U and Q. And how well does the SPT calibrate for the leakage?
So right now we're at sort of the percent level. I think it's around 2% is how well we measured it. So that's just where we are in our data analysis. There's nothing fundamental about that. It's just where we are. So what's nice about this measurement is that because it's a cross correlation between, so what we're using these other E modes, right? So what he's worried about is that, so you take these measured E modes, but we also have a map of measured B mode, and if there's some slight offset in your polarization angle, some of this E mode is going to end up in your B mode. And but by cross-correlating with this map right here has no knowledge of this map over here. And in particular, it knows nothing about these polarization angles. So if there's some small offsets that some of this map is leaking in, so you then muck around with that map using this, and any leakage, this map over here doesn't know anything or knows very little about how much of this map got mixed out. So by doing a cross-correlation of this sort of predicted B map with our measured one, any polarization angle mistakes are at most second order. And so we did tests where we basically just completely turned off all corrections for the polarization angle, and the signal is just completely invariant to that. So it's because of this cross-correlation that we're insulated from that. But that's another thing that's going to make it hard, that even once you get the noise level down to measure the B mode signal, which I will tell you that we have the sensitivity to measure that B mode power spectrum already, and we see stuff. But the polarization angle for measuring that's a much more stringent test.
Any other questions?
So in the detected B modes, the peak was around L500.
That's okay. So this is multiplied by L. So this is L times CL. So I'm not sure why Duncan chose to plot it that way. And these other things that I was showing you were multiplied by another power of L. Generally, things get plotted as L squared CL. So if you take this and you tip it up by another power of L, then that's going to move this peak out a little bit.
Okay, because it looked in a predictive one like that, it'd be at higher L, you should expect more power.
Yeah.
So is this,
It's a different scale. So this scale right here is from this, some cut off down here, but it's going out to L of 2500, whereas those other plots that I was showing you. So you can see this peak is right around 1,000.
Okay.
So imagine if you took that other, so if you divide this by 1 power of L, that's going to tip this thing down a little bit, and it's just going to slide this peak. It's basically the same curve.
Since you have improvement in the new detectors, I just wonder, how much improvement you will have on this. Can you actually directly see it, not using the
So
predicted ones?
So where we are with our noise levels, so the peak of this thing, if you were to convert this into a sort of an RMS noise, this peak is about in an arc minute pixel, which is our size of our resolution, this peak would be about 5 microkelvin. And that's roughly the noise that we're at with the current generation, is around 5 microkelvin. So we're going to get to the point where in terms of imaging these B modes, we'll have a signal noise of about 1 for imaging these B modes. So it's not going to be a high resolution map. But in terms of detecting the power spectrum, yeah, so we can already do that. We should get a detection that's, so we'll effectively just be limited by the fact that we're only looking at a certain patch of the sky. So that's sample variance limited as we call it. But we'll be right around there. It's not going to be a super high, we're not going to have a super precise map of these B modes. We'll just kind of, we'll roughly be able to, if you squint, you'll see them.
How about the new one?
Well, the 3G
The 3G
one, yeah, so that's going to have a noise level that's more like 1 microK. So this is in power, which is squared. So we'll be about, we'll be at least a factor of 10 better in power. So the signal will be around here, and our noise level for 3G will be down about here. And the way that on this plot, the noise goes as a diagonal line. So our noise level will be somewhere, I don't know where it's going to come across, but yeah, it'll look something like this. And so this is a 5 microK, so it'll be down by a factor of about 10, and it'll come down there. So that's where we're headed with 3G.
This graph, that it seems that if one is interested in the gravitational radiation in the early universe, then one needs to measure at the L.
At low
Yeah,
L,
at low
yeah,
L.
so.
So what is the challenge of obtaining those observation data?
So the main challenge, so the main challenge is, so if you go down to, so one challenge is that if you're on the ground, there's sort of a limited amount of sky you can look at. So you're not going to be able to get down to here. So getting down to here, so we actually already get down, this is pretty easy to do this part right here. Getting down to L of about 50, I think what we're limited by is the atmosphere, is fluctuations in the atmosphere. So as you make your map of the sky, you see, there's effectively clouds that are moving across the sky, and they're millimeter wave emitters. And so you have these sort of millimeter wave emissions that are moving across, and as they move across, you're scanning across the sky, and that just is going to propagate into your time stream. And so in principle, the sky is not polarized, or it should be very, very weakly polarized in millimeter wavelengths. However, because you're doing some measurement, the only way to measure we're measuring the temperature field. We're measuring, Stokes Q and U, which means we're measuring how much power is this way versus this way, which means you have to measure this and measure this, and each one of these is sensitive to these atmosphere fluctuations. And so you have two big numbers that have to be subtracted, and so then you have to worry about these polarization angles and things like that. And so you always get some leakage that'll propagate its way into your polarization map. And the atmosphere is very red. Fluctuations in the atmosphere are always bigger on larger scales. So as you go to larger scales, you become more sensitive to these atmosphere fluctuations. So and that's sort of, we think that we're going to crap out around 50 is where we're going to have problems getting below with SVT. But that's, as you can see, that's fine. We should be able to see the signal in principle if it's up here. And if it's not up here, once it gets down to here, then first you have to subtract out these B modes. So eventually with 3G, we're going to be in this regime where this signal that right now we're super excited to be detecting is actually just getting in the way, and we have to remove it. So we have all sorts of ideas for ways to get rid of it, but if you want to get rid of it, you first have to measure it, which means you need high resolution. So for getting rid of this lensing contamination, you actually need high resolution. But then you need to then measure on large angular scales. So it's, you can see the challenge of, it's just, you need a big dynamic range.
If you put into space, satellite?
Yeah, so there's an idea for CMB pole. It's been kicking around for a long time. So there's different variants of it, but opinions differ on whether we should launch something now and just hammer on it, or whether maybe it might be better to see if first why don't we just go from the ground and get as far down as we can and see if we see it, and then we'll have a better idea of what to look for when we launch the satellite. Because it's a lot cheaper to do this from the ground than to launch something into space. So there's sort of two schools of thought of, well, let's just get on this right now and get a big satellite up there. And other people are saying, we're actually, all of these upper limits have come in the last, so there's stuff on here that goes back 10 years. But it's only in the last sort of 3 or 4 years that we've really started marching down. So we're really only now beginning to push these limits down at a rate that's interesting. So I'm of the school of thought that I think we should wait a few years and see if we see something, and then have a better idea what to look for. But reasonable people can disagree on